So two more examples of problems you might see on the AP test where we have to find the area in between two curves. Here for 2013, I have two functions. One is quadratic. I can tell it's quadratic because I have x squared. And the other one is a cosine curve stretched by a factor of 4. So maybe one tricky part in this problem is, can I figure out which of these curves is on top? So I noticed that if I were to try to draw in infinitely many, infinitely thin rectangles, imagine those are all vertically oriented, does the top of my rectangle always touch the same curve? Yes, the top of my rectangle always touches that curve. And is that my quadratic function with a positive coefficient? No, because it kind of goes upside down. So that's my cosine curve. And the cosine curve is called g of x, so I can tell that g of x is the top curve. And the bottom of my rectangles did in fact touch the same curve every time. So bottom function is g of x. So I know that I'm going to be able to integrate g of x minus f of x. Notice please, technically that needs to go in parentheses or some kind of grouping symbol so that it all gets multiplied by dx. And my lower limit, so I'm integrating with respect to x, my lower limit is going to be the furthest left x that gets touched by this graph. They're not going to mess with you with the graph. If that looked like those two curves intersect where x equals 0, they do. And where x equals, what was it, 4? Oops, that was not the right choice. 2. There we go. So this is going to be from 0 to 2, g of x, top curve minus bottom curve, dx. If you wrote that integral, that's probably worth 2 points. It's probably worth 1 point for getting the correct integrand. That means not messing up the order of the subtraction too much. And getting the, that's probably worth 1 point, and then 1 point for the limits. So once you've written this integral, the hard work on this problem is not a calculator problem. We're going to have to evaluate this integral by hand. All right, so here's what I do. I've decided I'm going to integrate from 0 to 2, top curve minus bottom curve, so that's g of x minus f of x. I wrote that out. This is worth a point even if you don't write out the function rules for g and f. But now that I'm going to have to integrate by hand, I'm going to write out the function rules. I split my integral up into 2 parts at the subtraction sign, which is not required, but I'm kind of looking ahead and I'm thinking about integrating 4 cosine of pi x over 4. I'm thinking I don't know that antiderivative off the top of my head. But the second half, f of x, that's going to be pretty easy to find an antiderivative for because that's polynomial. So that I can make a u substitution in one part of the integral, but without having to make a u substitution in the easy part, I'm going to split this up. So this is what I have so far. Just think about that next line. So I know I'm going to integrate from 0 to 2, 4 cosine pi x over 4 minus the integral from 0 over 2, the integral from 0 to 2 of 2x squared minus 6x plus 4. The first integral needs a u substitution. So I'm going to make my u the inside of those parentheses. So pi x over 4. So pi is just a multiplier. 4 is just like multiplying by 1/4. So du is just a constant multiplier, pi over 4 times dx. So what I like to do is then isolate the dx. So I'm going to multiply by the reciprocal, 4 over pi. I'm going to get 4 over pi times du equals dx. So I'm going to come down to this integral. I'm going to change my limit. So if u equals pi x over 4, and my old lower limit was 0, my new lower limit is going to be pi over 4 times 0, which is still 0. That's how I got that lower limit 0. my new upper limit is going to be pi over 4 times the old upper limit was 2. So it's going to be pi over 4 times 2, which makes pi over 2. That's how I get that upper limit. So for me, changing limits, I find it to go faster. You have no obligation to. If you wanted to leave the limits off and put them back at the end, once you found the antiderivative and put your u back, that's fine. But I changed my limits. So now I'm going to be able to find an antiderivative for 4 cosine u. Well, the derivative of a sine is cosine, so the antiderivative of cosine must be sine. So my antiderivative is going to be 4 sine of u times this 4 over pi. So that makes 16 over pi sine of u. All right, I'm going to erase that. And then I'm going to subtract my other antiderivative evaluated from 0 to 2. So probably if you wrote this much, that was worth 2 points. If you can write antiderivatives, that antiderivative might even be worth 2 points, but it's worth at least 1 point. And we're going to have one more point at the end for the final answer. All right, so my work over here just shows that I'm going to evaluate both those antiderivatives from 0, well, the one antiderivative from 0 to pi over 2 and the other from 0 to 2. So this is just replacing u with pi over 2. Sine of pi over 2 is 1. Sine of 0 is 0, which is how I end up with just 16 over pi and nothing else there. I'm going to have to evaluate that polynomial antiderivative at 2 and at 0. Luckily at 0, I get just a whole bunch of zeros, so that's going to cancel out. So final answer, 16 over pi minus 4/3. You won't get full credit for writing this answer because the sine of pi over 2 and the sine of 0 need to be simplified. If you'd written this answer, that would for sure get full credit. The only time you would need to go this far to simplify is if this were the multiple choice section and you needed to choose a multiple choice answer. They would never make a question like this, multiple choice. Too many spots to go wrong, too many spots where you could go wrong, which doesn't test your calculus, it just tests sort of your algebra skills. So I strongly encourage you to stop when you get here. All right, this last one's a good one. I'm going to try to find the area of R. Really, really, really strongly suggest that you try this when you need to answer a question like this. I'm going to practice drawing in my vertically oriented rectangles. Imagine those are infinitely thin rectangles. And I want to ask myself, when I draw those rectangles, did all of the bottoms of those rectangles touch the same curve? Yeah, all the bottoms touched y equals 0. Did all of the tops touch the same curve? Well, these rectangles had their tops touch this curve, which I find out now is y equals natural log of x. And these other rectangles over here touch the line 5 minus x. So I don't have the same top curve for all of my rectangles. So I need to make a plan. I have 2 choices. I can try to break this picture up so that I find multiple areas which I can add together. And when I stop and find one smaller area, I need to have the same top curve and the same bottom curve for the whole part of that graph. Or I could imagine rewriting this in terms of y. So let me break this up first. I'm going to show you how to break this picture up and integrate with respect to x. I'm going to show you how to integrate with respect to y, which will only take one integral. You don't have to do both on the AP test. You just pick one or the other, whichever one you prefer. And then we'll do part C. So here, if I'm going to break this up, I think that it's right here that the change happened, where I changed from having a top curve of natural log of x to having a top curve of 5 minus x. So the question is, where does that happen? Y equals natural log of x. Where does that intersect y equals 5 minus x? So you might look at that and be like, oh, it's about, and try to guess the answer. You can't guess the answer. If it's not clearly marked, if there's any doubt, you have to use your calculator and find out. The good news is calculator active here. So on my calculator, I'm going to graph y equals natural log of x. I'm going to graph y equals 5 minus x, and I'm going to use the intersection function to find out the x coordinate of that point. Since I need my final answer to be correct to 3 decimal places, I'm going to write that number down, that intersection coordinate, to more than 3 places. I'm going to suggest 5 places. All right, so I just went to an online calculator function, an online calculator site. Of course, your calculator can do this without any problem. There's some options if you don't happen to have a calculator at home. So I typed in those two equations, y equals natural log of x, and y equals 5 minus x. I chose this button for the intersection, and this tells me the ordered pair for that intersection. 3.6934, comma 1.3066. All right, so on the AP test, you have no obligation to try to solve that algebraically. You might write the equation that you're solving. So one y function is equal to the other y function. And then I got a solution. I care about the x coordinate where that change happens. So just to make my next step easier, I've given that x coordinate a name. So I said let a equal 3.693334. Now I'm going to integrate. My leftmost x is 1. The rightmost x of the first section is a. And then my second section, where the top curve is 5 minus x, goes from a all the way to where 5 minus x intersects the x-axis, which is at 5. So I can type these two integrals into my calculator, and I know that the total area is going to be the sum of those two areas. This is how I get my final answer. Remember, it's a calculated problem. You don't need to find antiderivatives here. Very clear. There's my answer. You might have noticed instead that you could have drawn your rectangles horizontally, in which case the left edge of every rectangle touches this curve, y equals natural log of x, and the right edge of every rectangle touches that curve, which is 5 minus x. So I can actually integrate with respect to y and write one integral for this area. The downside to that is I'm going to have to take these equations and isolate the x. So y equals natural log of x. I want to get x by itself. I'm going to have to exponentiate both sides. So e to the y equals e to the natural log of x. But e-ing and natural logging cancel each other out, and I get e to the y equals x. And on the other side, I'm going to add x to both sides. I'm going to get x equals 5 minus y. I'm still going to need that point of intersection. It's just this time I'm going to need the y coordinate of it, because I'm going to have to integrate from bottom to top. So that's from 0 to that y coordinate of right minus left. This is my right curve minus my left curve. I'll show you that written up. All right, so this is what I could have done. I took those two equations, which had both had y isolated, and I've isolated the x instead. So I get x equals e to the y and x equals 5 minus y. I'm going to integrate from bottom to top. This was just that same point I found earlier, except now it's the y coordinate I care about. So I'm going to integrate from bottom to top, right minus left. So if I type that in my calculator, notice I get the exact same answer as if I had integrate with respect to x, but this time it took me only one integral to do it. Watch this next problem. All right, so this time I've been told I have a horizontal line and that's going to divide that picture into two equal areas. So my line wasn't really very good. It's going to be something a little bit lower. Write but do not solve an equation involving one or more integrals whose solution gives the value of k. You really have a lot of options here. So however you think about this, go with it and just try to translate this statement into an equation. So you could, if you, there's like so many ways to think about it. So the area under k should equal the area above k. That's one way to think about this. You could instead think that the area under k is equal to 1/2 of the area of r. These are both good ways to start. So I'm going to write this integral. The area under k is going to equal the area above k. So I'm going to try to translate that into an integral statement. So I want to say that what I just colored in red has the same area as what I just colored in blue. This is going to be much easier. It might only be possible, actually, if we think about integrating with respect to y. So let me get this out of the way. All right, so if I tried to translate that last statement into an integral equation, I said the area underneath k is equal to the area above k. So if I think of the bottom half, I'm going to integrate with respect to y. That means I'm going to integrate from bottom to top. So that's that was the section I think I had colored in red. So the top edge of that is where y equals k, and this is right minus left. So the area under k is going to equal the area above k. If I'm going to figure out the area above the line y equals k, I'm going to iterate from k up to that top point, which we called b. What was it? B equal, I think, 1.306 maybe, something like that. And this is again right minus left. So this is an equation. It contains the variable k. We don't know how to solve it, but that's okay. We were instructed not to solve it. So it's one great equation you could write. Remember that so this is great. It gets full credit. You don't feel like you have to do anything more than that. If you wanted to think about it a different way, remember that the area of the whole region was, what, 2.985? So another equation that you could solve, that you could write, would say like, okay, well then half of the area underneath k, if that's supposed to be half the area, is going to equal half of this. So I could have written the area under k, 5 minus y minus e to the y dy, is equal to 1/2 of 2.985. This is another way, good answer to their question. We get just as much credit. It contains the variable k, and it contains one or more integrals. All right, so you have a handout that has, I think, 6 areas between curves problems. I've asked you to do 5 of them, so give those your best shot, and we'll see you in class tomorrow.